introduction to probability, how to identify the sample space of a probability experiment, and how to identify simple events, how to use the fundamental counting principle to find the number of ways two or more events can occur, distinguishing amongst classical, empirical, and subjective probability, finding the probability of a complement, of the complement of an event, not complement, but complement, and how to use a tree diagram. So, what do you think of when you think of probability? Like, what are some things that come to your mind when you think of probability? Odds. Yeah. Odds of winning something. You know, now that, football season is among us, Vegas bookmakers make odds on football games. And not just on football games, I found out. I would love to know, did Vegas have the Buccaneers beating the Saints yesterday? Because if they did, well, there's going to be some pretty unhappy bookies. Odds of winning, and then also, I also like to think of gambling. That's something you really shouldn't do. But I did it this past summer in Vegas, I lost $50, so I'll tell you, though, social distancing in casinos sucks. Like, the table's open or nothing. See, I don't go to play the slots, I go to play the tables. And here's another thing that I always came to enjoy as a youngster was game shows. The odds of winning. I want to show you something kind of nifty here. So a probability experiment is an action or a trial through which specific counts, measurements, or responses are obtained. The outcome is the result of a single trial. Sample space is a set of all possible outcomes of a probability experiment, and an event consists of one or more outcomes and is a subset of the sample space. So an example of a probability experiment could be rolling a die. An outcome would be 3. The sample space would be 1, 2, 3, 4, 5, or 6. Now, a lot of people would say, oh, just the 1 through 6, but technically it's 1, 2, 3, 4, 5, or 6. So probability is a big, big part of statistics. And I say that because there are entire courses, heck, entire fields of study devoted to probability. In fact, I'll show you a textbook I have. Let's see, probability. Where's this one? Like mathematical statistics, that's another name for it. Basically, probability is its own course. So it's a pretty big field of study. Basically, we're going to be making a thumbprint in the whole area of probability, but right through the heart, I like to say. So here's a guided example. A probability experiment will consist of tossing a coin and then rolling a 6-sided die. So the sample space, there's 2 outcomes when you toss a coin, a head or a tail. Now, possible outcome after each coin is rolling a 1, 2, 3, 4, 5, or 6. So one way to list outcomes for actions that occur is to use a tree diagram. And as you can see, this sample space is going to have 12 possible outcomes. Head 1, head 2, and all the way through T6. So, if, for instance, if a family had 2 children, the sample space is boy, boy in terms of their genders, boy, 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 girl, girl, boy, and girl, girl. Now, in this case, all 4 outcomes are equally likely. Now, if you're dealt 5 cards from a deck, a standard 5-card poker, if you're dealt 5 cards, and if we let S be the number of aces we get, so the number of aces can range from, we can have as few as how many aces in a 5-card hand? Well, we could have none. We could have 1 ace. We could have 2. We could have 3 or 4. But why would it end at 4? Because there's only 4 of each card in a standard 52-card deck. Now, I'm not going to turn you into card counters if that's what you're thinking here. I've actually done the research on card counting, like they did in that movie 21, and to win money, you actually have to put forth large sums of money. Like, you're not going to get rich betting like $20 or $25 a hand on blackjack. You got to bet like 1,000. That's not for me, no. So would you say these outcomes are equally likely? Definitely not, because, for instance, if you had 4 aces in a 5-card hand, what would you be doing? How would you bet if you had 4 aces? You'd probably bet everything. Because when you think about it, only one hand could beat you. A royal flush. And yeah, and that's not even possible. Well, you know what, a straight flush could, but now the chances of someone having a straight flush and somebody having a 4 of a kind, I don't know, something's really up with that. But yeah, if I had 4 aces, I would be going all in on that. Sometimes I've actually watched the World Series of Poker. I'm not as serious of a poker player as some of my friends are. Like my best friend from college, like we'd go to casinos, like he'd actually wear sunglasses because when you get a good hand, people can see the excitement in your eyes. So that's why they wear sunglasses and see. Yeah, maybe I just don't have the nerve to play like no limit poker where people are putting down like $100 or more a hand. No, that doesn't work for me. All right, so sample space for a single birth in terms of gender. Well, we could just have a boy or a girl. Now, for 2 births, in terms of gender sequence, we could have boy, 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 girl, girl, boy, or 2 girls. You could also have made a tree diagram, the first kid being a boy or a girl, and it follows the second one is either a boy or a girl. So then the outcome boy, 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 girl, girl, boy, and girl, girl. And you could also count the number of boys or girls, and we'll get into that a little later on. So I'm going to let you try this, where You have a spinner with equally likely values A, B, and C in a standard fair six-sided die. A sample space for the number for the outcomes for this. So let's say, for the spinner, it could land on either A, B, or C. And it follows from each spin move, you get a 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or 6. And 1, 2, 3, 4, 5, or a 6. So basically, the sample space would just be, A1, A2, A3, A4, A5, A6, A7, oh, not 7, B1, you sunk my battleship. So you spin your spinner. I like to play the spinners. They make good music. Probably never heard of the spinners. Very talented. So when all the smoke is cleared, there are 18 possible outcomes. So we're going to be dealing with simple events such as events that consist of single outcome. Now, they could consist of more than outcome. So if we roll a six-sided die and rolling at least a 4, that's technically not simple. So a simple event could be rolling a 3. A not simple event could be rolling a prime number. Now, I have one of the largest dice collections you may have ever known. I actually looked to see in the Guinness Book of World Records, this one guy has more than I do, but I have a pretty good collection. I have dice that have as few as 4 sides, and I do have one dice that's 150 sides. And no, I never really got into Dungeons and Dragons, but my friend and I, in one of our, back in college, we decided to try to see how Yahtzee with 20-sided dice would work. It took too long. But it was fun. Yeah, we're nerds. That's what math dorks like me do. All right, fundamental counting principle. If one event can occur in n number of ways, and a second event can occur in n number of ways, the number of events can occur in sequences m times n. So if we jump back to this, there were 3 outcomes for the spinner and 6 outcomes for the die. So that's another reason you could say there are 18 possibilities. So let's say you're purchasing a new car. Possible manufacturers, car sizes, and colors are listed. Now, of course, this is straight out of a textbook. I would have different options, but compact or midsize. What about cars for people like me? I'm not exactly a small guy. You could either get a Ford, GM, or a Honda. Ford, fix or repair daily. I joke. Compact or midsize, and white, red, black, or green. Yeah, every time, my first car was a 1987 Chevy Nova. Now, that was basically a Toyota Corolla chassis. And this is how I looked when I drove it. Like, my knees didn't come up that high, but it was not a comfortable car to drive. Let's just say that. But, you know, you may do. Then when that car blew up, thank God. I actually went older. I got an 85 Oldsmobile. Oh man, that thing was awesome. It was huge, too. Comfortable. So there are 3 choices of manufacturers, 2 car sizes, and 4 colors. So using the fundamental counting principle, we would have 24 different cars to choose from. So I'm going to make this a clicker question. If you're deciding on a wardrobe, so you could have 11 shirts, 3 pairs of pants, 9 pairs of socks, and 3 pairs of shoes. So I'm going to use my calculator because, well, it's here. You get 891 wardrobe combinations. You know, I have a lot of shirts. I mean, I do have some pairs of pants, but they're all mostly the same. All right, so 891 is the answer to this. So I want you to try the next one as soon as I get this clicker thing going. So yeah, you're going to go to Denny's. I wish there was a Denny's around. It's like growing up back home, there was a Denny's a third of a mile from my parents' house. We were regulars there. I'll tell you though, they always like to make fun of Denny's. All right, so there are 8 choices for your meat, 6 choices for your cheese, 5 options for your egg, 13 side options, and 12 choices for a drink. So yeah, you're definitely going to want to use a calculator on this. And you're going to get 37,440 options. Now, if I wanted to extend this, let's say you go to Denny's every day. Now, I know the Denny's by my parents, I'll tell you, I kid you not, they actually used to be open Christmas. My sophomore year of college was when the franchise got sold, and they actually decided to close on Christmas. And it was funny that they couldn't find the keys to the place. Like, they hadn't closed the place in like years, so they had to install new locks and everything. So let's say if you eat every day, 364 days a year. So if we took 37,440 and divided it by 364, you could get a different combo every day for almost 103 years. No, it is possible. Like, you started going to Denny's as a toddler, and yeah, go there every day. Like restaurant I worked at, we had our regulars, and it was, I want to say it was kind of depressing, like when we'd see like one of our elderly regulars not come in, and we'd then read his obituary. Oh man. Most of the time, they were pretty damn nice people. So, We're now going to talk about probability here. So A, B, and C and other letters will denote specific events. So instead of having to write out the probability that event A happens is 0.53, you could just write it as P of A equal to 0.53. You know, this is a nice little way to avoid writer's cramp. So a theoretical approach to probability assume that a given procedure has n different simple events, and each of those simple events have an equal chance of occurring. So basically, the probability that A can occur is the number of ways it can occur divided by the number of outcomes. Now, this all looks like fancy talk here, and this is probably complicating it. Let's say we roll a six-sided die. Now, for a six-sided die, and we'll assume it's fair. You ever heard of unfair or rigged dice? Have you ever seen Ocean's 13, where they rigged the casino games? That was pretty cool. So event A, rolling a 3. So since there is one way to roll a 3 over 6, the probability is 1 out of 6. So event B, rolling a 7. There's no possible way to roll a 7, so basically it's 0 over 6, otherwise known as an impossible event. Another example of an impossible event would be the Cleveland Browns winning a Super Bowl, or Pittsburgh Pirates winning a World Series. Rolling less than a 5. So the outcome, now pay attention to where it might say less than 5 or 5 or lower, because that would be two different things. So less than a 5, you have 4 different outcomes for that. So it's 4 out of 6, or 0.667. So let's say the probability, so now we're going to roll a 12-sided die. Yep, you heard it, 12-sided. You ever heard of a 12-sided die? I have. So the probability that we roll a 7 is simply 1 out of 12. And if we find the decimal equivalence, it would be 0.083. And technically, this 0.083 repeats. How about rolling an 11? It would be the same thing. There is one outcome that satisfies rolling an 11. Now, I'm going to make this a clicker question. The probability of rolling either a 1, 3, or an 8. So type in the decimal. What's that? Yeah, go ahead. All right, so a 1, 3, or an 8 means that there are 3 possible outcomes. So 3 out of 12, which does simplify to 1 over 4. which is 0.25. Now, how about greater than a 7? Well, we might want to list those outcomes. 8, 9, 10, 11, or 12. So that's 5 out of 12. And that is 0.416 repeating. How about not a 7 or 11? We're not rolling. We don't want a 7 or 11. It would be 10 over 12. Basically, yeah, everything except 7 or 11, which does simplify to 5 over 6, which I believe is 0.83 repeating. How about rolling an even number? Yeah, you could get a 2, 4, 6, 8, 10, or 12. So, yeah, 6 over 12, or 1/2, or 0.5. On your test or problem set, all I'm going to need is the fraction. Now, prime number. I like to throw that in there just for fun. Remember, a prime number is a number that is divisible only by 1 in itself. So we'll count 1 and 2 as prime. In fact, I'm going to make that a clicker question in about a minute. And just round to 3 decimals on the clicker. Give you a 30 on that. So the possibilities for prime numbers are 1, 2, 3, not 4, 5, 7, 8, 9, 10, or 11. So basically that is 6 over 12, 1/2, or 0.5. All right, so another probability calculation we're going to see is empirical or statistical probability. So, got an example here. Yeah, this is where frequency of the event over the total frequency. Now, this isn't new because we actually did something like this in the last unit when we were doing our pie charts. So, if we surveyed 1,504 people at random, the probability that the next person surveyed has a positive overall impression would be 406 out of 1,504. So, here is a grade distribution of students who have taken organic chemistry. Now, the first thing you should probably do is add up the total number of students. When you do that, what do you get? You get 2,000. So the probability that somebody gets a C, 912 over 2,000, is 0.456. Probability that someone gets an A, not very often. You get 0.057. Now, I'm going to make this a clicker question. What is the probability that a randomly chosen student passed the class? And well, it is a lot of work. So basically, passing means A through D. So you have 114, 305, 912, and 581 all over 2,000. Basically, that would be 1,912 over 2,000. Is that right? So we get 0.956 for this. Now, the probability that a randomly chosen student flunked the class is 88 out of 2,000. Which is 0.044. Now, if you do me a favor real quick, if you take 0.956 and 0.044 and add those together, what do you get? You get 1. Basically, this is going to be kind of a good example. This is all possible events of a problem. All possible events have to add up to 1. So passing class and failing, that would add up to 1, or 100%. I could have also done 1 minus 0.044 for the for the passing. Or for the failure, 1 minus 0.956. We'll talk about that a little more formally in a few minutes. But basically, this is an introduction to the complement rule as it pertains to probability. Now, the last type of probability that I'm going to talk about, well, not yet, law of large numbers. Basically, as an experiment is repeated over and over, the empirical probability of an event approaches the theoretical or actual probability of an event. So if we toss a coin so many times, it's going to approach the theoretical probability in large numbers. Count Buffoon tossed a coin 4,040 times and wound up with 2,048 heads. In 1900, this English statistician Carl Pearson tossed a coin 24,000 times and got 12,012 heads. While imprisoned by the Nazis during World War II, John Jarrett, South African mathematician, tossed a coin 10,000 times. That's before we had Facebook and social media to distract us from this stuff. So that's how that'll work. Now, subjective probability is arrived at by intuition, educated guesses, and estimates. For instance, a doctor may claim that a patient has a 94% chance of survival, or it may be claimed by certain news media like Fox News that Donald Trump has a 71% chance of being elected as president. That's subjective, based on intuition, educated guesses, and estimates. Now, I am very skeptical of subjective probabilities in a lot of ways. So, would this be theoretical, subjective, or empirical? The probability that you get the flu is 0.71. That's subjective. Now, here's the thing. 13 years ago, when I was a young teacher, first starting out, they said, oh my God, you're a first-year teacher, you're going to get sick a lot, and you should get a flu shot. Well, I'll tell you, I got the flu shot, and I got so sick that, yeah, I missed, basically, yeah, I went into work. I should not have gone into work that day, but I can tell you the number of days I've missed from being sick, I can count on one hand, because I generally don't get sick. But yeah, that was the only time I ever got a flu shot. Probability of a hurricane hitting us is 0.24. That's subjective. Yeah, of course, 4 years ago, when my wife and I first moved here, we got Hurricane Matthew. Bless you. Now, it wasn't so bad, though, at least, because it at least happened towards the end of September, if I'm not mistaken, and it wasn't brutally hot and humid like it was 2 years ago with Florence. Oh, that was horrible. How about the probability of a voter chosen at random under the age of 35 is 0.32. This is empirical, based on data, and probability of the person chosen at Wayne Community College as female is 0.53. That is also empirical. Now, the probability of winning a big three with one ticket is 1 in 1,000. Oh yeah, the big three lottery. That's theoretical. And probability of winning a car with 3 tickets is 3 out of 500. Yeah, theoretical probability. I remember I put in an entry to win a car, and I actually got a call back saying you've won. However, we need $1,000. Like, no. Because when you win, you've got to pay taxes, but not up front. Now, when you do win something like that, you should get like a tax form. I don't know what the proper term is. You know, to W something. But yeah, when you win, because I watched this documentary, I grew up big on game shows because, well, there were no kids in my neighborhood, and that's all I really did was sit in my parents' basement and watch game shows all day. Yeah, my life was boring. But yeah, like they had a documentary about this one guy, like he won a car and basically he got a tax bill and it got treated as taxable income, so he had to pay on the income tax. which seems fair, I would think. All right, so a little more about probability. Probability of an event is a number between 0 and 1 that reports the likelihood that the event will occur. So if we call this event A, probability of an event being equal to 0 means it's impossible. That is, such as the Pirates winning a World Series, or on the other side of the coin, if the probability of an event equals 1, that means it's a certainty, such as Tom Brady cheated. So basically, impossible all the way to certain. So the probability can be between 0 and 1 inclusive, and even chance 50-50. So the something has to happen rule, the sum of all probabilities of all possible outcomes, has to equal 1. Now, we already kind of established that with the pass and fail for organic chemistry. Now, the complement rule, probability that something happens is 1 minus the probability that it does not happen. So if we have an event A, we have the complement of A. Now, it's been labeled as A with a C or an overbar. I've seen that in a few textbooks. And A prime is what your book would use. Now, even though we're not officially using the textbook, I would like to take a second and show you what I'm talking about here. So if I do this real quick, MyLab stat. So open your MyLab. And e-text, and view the e-text. And basically, you do have a textbook at your perusal here. Okay, so contents. So yeah, you can switch between pages. That's 130. And complement. Yeah, see, your textbook actually uses the prime symbol. A textbook I once used actually used a C. But basically, the probability that an event does not occur plus the probability it does occur does add up to 1. And you can arrange this in other ways if you so desire. So let's say we sample a survey, or survey a sample rather, of 1,000 employees at a company and record the age of each. So we want to find the probability of randomly choosing an employee who is not between 25 and 34 years old. So one way to do this is to use the complement rule. Basically, you subtract from 1 what you don't want and get 0.713. Or you could add up all of the probabilities and get it. So in other words, it doesn't matter which way you do it. I'm going to, it's perfectly acceptable either way which one you do. All right, so what I want you to do now is, this is going to be a clicker question. Find the probability that you choose an employee who is not 65 and over. All right, so not 65 and over. So basically, we could add up all the people that are not 65 and over and get 820 out of 1,000 and get 0.82, or 1 minus 0.18. But either way, we get the same thing. All right, how about 35 and over? Make that a clicker question. Give you 30 seconds. Okay, so 35 and over. So what we can do here, we can add 314 plus 74. What's the next one? 41 and 180, and get 609 out of 1,000, which becomes 0.609. All right, how about 54 or younger? So for 54 or younger, well, what I could do is just do 1,000 minus 41 plus 180. And get 779 out of 1,000. So that would be 0.779. So here's another you try. I'm going to have you do the second one in the clicker. So basically, they surveyed 200 inmates in a state prison and found that 123 of them had committed their first crime as a juvenile. So I'm going to have you enter this second one in the clicker. Yeah, what was that shit? Yeah, Beyond Scared Straight. I'll tell you, I always enjoy watching that. So the probability that one was a juvenile delinquent is 123 out of 200. Which would be 0.615. So what we could do is, if 200 were juvenile delinquents, and I mean, yeah, 200, we had 200 delinquents, and 123 of them were juveniles, 77 of them were not. So 77 out of 200 which would become 0.385. So that's how that'll work. Now, even though we do have a few more probability exercises to cover, I do want to, so yeah, it'll be 0.07. So show that this is a legitimate probability model. Now, I'm only going to ask this question here, but basically all probabilities add up to 1. And here's why. In fact, I think it was the first time I taught this as an adjunct back in Virginia. I had this on a test, and I said, explain why this is a legitimate probability model. And this girl who was taking stats for the 3rd time, and she was very bitter. And she actually wrote, I don't see why you bothered to ask this question, because if this was not a legitimate probability model, none of the other questions would be able to be answered this time. And and she actually did apologize. She said, I'm just so infuriated that I'm forced to take this particular class by the powers that be. And she let them know in my final evaluation. I can tell who wrote her end of semester evaluation. But yeah, I stopped asking that. So find the probability that the chosen student is not in the traditional age group. Well, we could just do 0.32 plus 0.12 plus 0.07, which is going to be 0.51, or we could do 1 minus 0.49. Now, find the probability that a chosen student is not 60 or over. So that's actually very easy. We can just do 1 minus 0.07 and get 0.93. Or we could have added all of these other ones, 0.49, 0.32, and 0.12, and gotten it that way. All right, I'm going to let you do the last one on the clicker. Get 30 seconds on here. All right, so not between 30 to 59. So basically, you could just do 1 minus 0.12 and get 0.88, or you could do 49 plus 0.32 plus 0.07 and get it that way too. So that's how we can do that here. All right, so moving along, let's say we have 4 children, and we're going to let X be the number of boys. So the sample space for X is going to be, and keep in mind, this is the number of boys. We can have as few as how many boys? We can have no boys. We could have 4 girls. We could have 1 boy, 2 boys, 3, and even 4 boys. Now, we're going to make a tree diagram here, and we're going to make, with that, a probability table. So, this is where, yeah, it's going to take a little bit of time here, but here's X, the number of boys. And probability of X. So 0, 1, 2, 3, 4. So we can make a tree diagram, and and then the final outcome, for the second could be a boy or a girl, or a boy or a girl. For the third, and then for the fourth, and then the outcome so boy, girl, girl. And then for the fourth one, that could be a boy or a girl. So basically, you could have 4 boys. Or you could go boy, 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 girl. So I'm going to give you a couple of moments to finish that up. So we'd have boy, boy, girl, boy, and boy, boy, girl, girl. So boy, girl, boy, girl. So boy, girl, boy, boy. There is actually going to be an easy way to do this in the next section. Boy, girl, boy, girl. Boy, girl, girl, boy. And then boy, and then 3 girls. So there's 8 of our outcomes right now. However, when the smoke clears, we're going to have 16 of them. Now, these probabilities are all going to be divided by 16. So girl and then a boy. Actually, I'll move this down a little. You could have a boy or a girl. Boy or a girl. Boy, girl. 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 Boy, girl. So girl, and then 3 boys. Girl, boy, boy, girl. Girl, boy, girl, boy. And then girl, boy, then girl, girl. And for the last 4, girl, girl, boy, boy. Girl, girl, boy, girl. Then girl, 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 boy. Then lastly, 4 girls. So, next to the outcome, we'll have the number of boys. So, So for the number of boys for this one, obviously there were 4 boys. And in this next one, boy, 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 girl, how many boys were there? There were 3. There were 3 here, then there were 2. There were 3, 2, 2, and 1. 3, 2, 2, and 1. 2, 1, 1, 0. So the probability that we had no boys is 1 out of 16. And probability of 4 boys was 1 out of 16. Now let's look at 3 boys. So how many different ways did we have 3 boys? We had that 4 different ways. Now, how about 2 boys? 3, 4, 5, 6. So there were 6 different ways we had 2 boys. And how many ways did we have 1 boy? We had 4. Now, if you add these probabilities up, what do they add up to? 16 out of 16, which ultimately is what we wanted. They'll add up to 16 over 16, which is 1. All right, so here is a clicker question. Probability of 2 or more boys. In 1 second here. 1 minute. Okay. And just take it to all 4 decimal places. All right, 30 seconds on that. 4. So the probability of 2 or more boys, basically, it's 6 plus 4 plus 1 out of 16, which is 11 out of 16, which is 0.6875. All right. Last one here. Hold on, not yet, not yet. All right, clicker for that. Give you 30 on that. right, so for this one, probability of at least one boy, we could just do 1 minus the probability of none. So 1 minus 1/16, which is 15/16, which happens to be 0.9375. All right, so that's where we're going to stop today, and we'll pick up the rest on Monday, on Wednesday. We want to toss a head and then roll a prime number. So we have to consider just the head here and then a 1, 2, 3, 5, or 7. So basically 1, 2, 3, 5, and 7. So that's going to be 5 out of 16, which is going to be 0.3125 for this. So that's what you'll get. All right. So here's another you try problem. We'll do a bit more probability practice here. What we would do here is divide each of these by 1,000. So basically, 145 over 1,000 would just be 0.145. And then we'd have 0.327, 0.378, 0.111, and 0.039. Some people might answer 0.39. 39 over 1,000 is 0.039. Now, if you added all of these together, it would add to 1.00 or 100%. So, the probability that a randomly selected student earns a B, well, that's simply 0.327 or 32.7%. Now, here's the thing. I would accept either one myself. So the probability that a student flunked the course, well, that's easy, 0.039. Failed, F means failed. Now, pass the course, there's two ways to figure this out. What you could do is you could add 0.145 plus 0.327, 0.378, and 0.111. And for that, you would get, I believe, 0.961. Might there be a slightly faster or more efficient way to do that? Subtract 39 from 1,000. So what you could do here, or 1 minus 0.039. Boom. Now, a randomly selected student was above average, earning an A or a B. We get 0.145 and 0.327. So when we add that together, we get 0.472, or 47.2%. I would accept either one. All right, so not bad there. So. All right. So we're now going to talk about students of many ages enrolled at a local community college. Now, by the way, you're going to put this one in the clicker, and you can do so now. So the first thing you got to do is find the probability that the person is in the 55 or older age group. So what would that be? 0.01. Well, that's a small percentage, but there are. In fact, I think this is one of the first semesters I've actually taught here where in any of my classes I don't have a student that is older than I am. Every semester I've always had a student that was older than I was. Now I've had some that were old enough to be my mother or father. Grandfather, well, my grandfather were alive, he would be 113. And basically my dad was 7th out of 8 kids. They had my father late, and my father, they had me late. So he was already in nursing care when I came around. But that's okay. Find the probability the person chosen is under 21. So we can just add the probabilities of 0.06 and 0.59 to get 0.65 or 65%. How about a student being 26 or over? Well, just add those probabilities and we get 0.12 or 12%. 18 or over. Now, there are 2 ways to approach that one. I could add all of the probabilities that go with that, 0.59 plus 0.23 plus 0.08 plus 0.03 plus 0.01, and I get 0.94. Or I could just take away what I don't want. 1 minus the probability that they're younger than 18. Youngest person I've seen in a college class was, I had a 10-year-old. There was a 10-year-old in one of my classes when I was a senior at Pitt. Yeah, I'm not kidding you. Well, he was the son of a professor, and this kid was like a budding genius. Like homeschooled, and long story short, like he basically had no life. Like his life was just do math. Like they didn't let him play video games, watch TV, nothing. But he ended up graduating with his bachelor's degree in math when he was 16. And he got a doctorate a couple more years later from Harvard. So, but still, you gotta let a 10-year-old be a kid. So 21 and 54, we add those probabilities, 0.23 plus 0.08 plus 0.03, and for that we would get 0.34. So that's how that'll work. Any questions on these? Nothing. And we're not dividing these because you have the outright probabilities. Okay, so if I gave you a set amount, like in the previous example, you would divide by how many you had. So that's a good question, very good question. But there are some cases where you are outright going to be given the probabilities. And in that case, you just add them. There's no such thing, well, there is a such thing as multiplying probabilities, adding overlap and such, but that's beyond our pay grade. Adding probabilities that don't overlap, that's something that we're doing here, obviously. But like multiplying them, yeah. I mean, that's something we could do, but that would be like a stats level 2. All right, so your college ID number consists of 8 digits. Yeah, when you go off to some big state university, and I love the ones that say you're more than just a number. No, you're just a number. You might as well have it tattooed on you or something. I mean, they used to use social security numbers when I was an undergrad student. They stopped doing. A lot of state schools stopped doing that in the mid-2000s because of identity theft concerns. So I had we used PeopleSoft, and I never did memorize it. I actually wrote it somewhere. So what is the probability of getting your college ID number when randomly generating 8 digits? Now, 8 digits, and each digit is 0 through 9. So, using a fundamental counting principle, there's 10 possibilities for each entry. So, what happens is you just multiply those 10s, and you get 100 million possible ID numbers. And only one of those corresponds to your ID number, 1 out of 100 million. Now, let's say Stewie Griffin, in an early episode of Family Guy, he calls home in Road to Rhode Island, and he starts with 111, 1111. Lois? There. 111, 1112. Lois? 111, 113. Lois? So if he tried all possible phone numbers, what is the probability that he gets Lois? Now, for starters, he really should have been doing zeros. But we're going to see that that really doesn't work in just a second. So 7-digit numbers. Now, of course, we're not used to 7-digit numbers. Back when this episode aired, I think that was actually still in the 90s, we still had 7-digit numbers. We didn't have to deal with area codes. So there are 10 possibilities for each phone number. So basically, there's 10 million possibilities. So he would actually have a 1 in 10 million chance, or 1 out of 10 million chance. Now, thing is, Stewie and a lot of people don't realize the first digit cannot be a 0 or a 1. So phone numbers are of this form, BCC, CCCC, where C is any number 0 through 9, and B is any number from 2 through 9. So for that first digit, now there's 10 possibilities for the remaining 6. But how many possible numbers are there for that first digit? 2, 3, 4, 5, 6, 7, 8, 9. 8. There's 8 of them. So in reality, there are 8 million 7-digit phone numbers. So, but still, odds are pretty slim. Probability that he gets Lois. I just love how he would call his mother Lois. Like if I called my mother by her first name, I get slaughtered. See, it's funny, when I'm particularly stubborn, or my dad can be one of the most pig-headed people you've ever met. And, I can get that way sometimes too. My mom and my wife will say, all right, Dan being my father's name. So, okay, Dan, you're always right. But in actuality, my dad is actually right a lot of the time. So that's how that works. Now, prior to 1998, so that puts a lot of you, oh damn, most of you weren't even born yet. Pittsburgh metro area had one area code, 412. given the phone numbers are of this form, and B is any number from 2 to 9, we know that there were 8 million possible phone numbers prior to 1998. Now, I don't know if any of you have ever lived through like having your area code split, but this is what happened in the Pittsburgh metro area. And here's why. Cell phones were becoming prevalent and dial-up internet. So people were getting, how many of you have ever used that dial-up internet where it makes that annoying sound? Yeah. A lot of people would get second dedicated phone lines for internet. But now with the advent of DSL and cable internet, that wasn't a necessity anymore. But cell phones, but now we're not splitting, we're not really needing to split area codes, because let's say you have a cell phone and you get it cut off. You actually, within 30 days, if you don't pay to have your service restored or whatever, they can actually take your phone number and give it to someone else now. They didn't used to do that. So in 1998, yeah, so that's when Pittsburghers had to start entering area codes. So when they added a second area code, how many numbers were available altogether when they got a second area code? Well, there's 8 million for the original, 8 million new. So you have a grand total of 16 million numbers. There was only one state, the last state, that had only one area code. Anyone want to guess what it was? They actually had to split it recently. Anyone want to take a guess? West Virginia. Insert random West Virginia joke here. All right, so now we're going to do one of these problems with 2 6-sided dice. So what would the probability be that we roll a 5? Well, question is, how many cases are there where we have 5? There are 4 cases, so it would be 4 out of 36, which does simplify to 1/9. How about rolling a 7? 6 out of 36, which happens to simplify to 1/6. How about rolling a 10? There are 3 ways to do that. 3 out of 36, which simplifies to 1/12. Now, less than 8, so does that mean we actually include the 8? No. So we count all the possibilities here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 out of 36, which nicely simplifies to 7/12. Now, 7 or 11, you would just add the probabilities together. Now, the probability that you get a 7, well, we already figured that out. is 6 out of 36. Let's not simplify until the end. And how about 11? 2 out of 36. So when you combine that, that gives us 8 out of 36, which happens to simplify to 2 over 9. Yeah, I mean, so in a more advanced class, we could actually subtract overlapping probabilities, but see, we're not doing that. So interestingly, the significance of 7 or 11 is what you would win on an opening roll of craps. Now, 2, 3, or 12. Well, a 2, probability of a 2 is what? 1 out of 36. How about the probability of a 3? 2 out of 36. And 12. So this becomes 4 out of 36, or 1 over 9. Now, that's called craps. That's if you crap that. What is the probability that the sum is greater than 9? I want greater than 9. 6 out of 36, which is 1 over 6. How about rolling a 13? Can I roll 13? No. So 0. Impossible. Which sum is most likely to occur? A 7. What's the probability? Yep, probability is 1 out of 36. No, 6 out of 36, or 1 out of 6. Now, there are 2 sums on here that are the least likely to occur. What are they? 2 and 12. And the probability of each is 1 out of 36. So basically, yeah, that guy that rolled that 2, I mean, if he rolled, that was just pure luck. All right, so that will conclude our part on probability basis. Now we're going to get into something a little more advanced, where we're going to be talking about discrete random variables, discrete probability distributions, how to find the mean, variance, and standard deviation, and expected value. Bless you. So random variables are variables that are based on outcomes of random events. They're denoted with capital letters, such as the number of heads in 3 coin flips. Now, these are part of probability distributions, which they're descriptions that give the probability for each value of a random variable, often expressed in the format of a graph, table, or a formula. So, if we can list all possible values of a random variable, that's what we would call a discrete random variable. So basically, you think of integers. Discrete random variables are either a finite number of values or countable number of values. But, I mean, there could be infinitely many, but, you know, we'll have bounds with this. For instance, some examples like this could be the number of heads in 3 flips, number of males in the next 10 births, or the ages of the next 5 people to walk through the door. Now, continuous random variables they're still denoted by a capital letter, but now think of real numbers, and they have infinitely many values, and they can be associated with measurements on a continuous scale without gaps or interruptions. Now, we're not doing continuous random variables here. That's basically what the normal distribution is all about. So, we're only dealing with discrete here. So, in order for a probability distribution to be valid, there has to be a numerical random variable x, and its values are corresponding with, and its values are associated with corresponding probabilities. Now, the sum of all probabilities has to add up to 1. And each probability has to be between 0 and 1 inclusive. So, and again, we're only going to be dealing with discrete random variables here. Chapter 5, or Unit 3, will deal strictly with the normal distribution, which that's a continuous distribution. And in fact, there are numerous continuous probability distributions that are out there besides normal. And there are numerous discrete ones too. We're going to do discrete random variables. We're also going to do binomial, geometric distribution, and the Poisson distribution. However, there are other ones such as hypergeometric, gamma, delta, but yeah, we're not touching any of that. That's like stats 5. So we're going to construct a distribution from the ground up, find the mean or expected value. So when I say mean or expected value, they mean the same thing. Variance and then standard deviation. Now we'll make a frequency distribution, find the sum of the frequencies, which usually will be given to you. Find the probability by dividing. So this is when you may divide. You also may be given a case where I might give you the probabilities outright. You never know. Check that each probability is between 0 and 1 and that the sum is 1. So, an industrial psychologist administered we're going to build this entirely from the ground up. So, he's going to administer a personality test for passive-aggressive traits to 150 employees, where they're scored 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. So we're going to construct a probability distribution and graph it. Now, we're not always going to graph. So the total number of individuals was 150. That will, in all likelihood, be given to you, but you might have to add that. But it will always be a nice, clean number, like maybe 100, 200, 500,000, up to 5,000. Because, 5,000 easily. In other words, all the probabilities will be terminating decimals, because I hate dealing with repeating decimals, especially with this stuff. So score of 1, there were 24, so we divide each of these by 150. When you add the frequencies, you got 150, and all these probabilities add up to 1, or 100%. So far, so good. Now, we can also write this as a horizontal table if we want. I actually prefer writing them as a horizontal table. Why? That's just the way I am. A histogram of this will look like this. So using this information, we are going to find the mean or expected value. Now, you look at this formula and you might think, oh crap, this looks really confusing. But, mean is represented either by mu or E of x. It is the sum of the individual score or individual value times the corresponding probability. You find those products and you add them all together. There is your expected value. Plain and simple. Now, I'm going to do this one showing each individual little calculation. You do not have to go this deep each time. Why? Why am I doing this? To show you where everything comes from. And if you're lucky, I may show you some calculator tricks. So to find the mean of the above, we calculate. Ultimately, the sum, the score of 1, the probability was 0.16. Score of 2, the probability is 0.22. Score of 3 times the probability, score times probability, add them all together and we get 2.94. So that is the mean score. Now, I want to show you another way that this can really make sense here. I'm going to punch this up on Excel. So, how many people out of the 150 scored a 1? There were how many? That was the probability, but actually how many? 24. We had 24 ones. So, I'm actually going to write this down. Take this down, fill it down, and I have 24 ones. Now, how many people got 2s? 33. So I can actually do it this way. Fill down, there's 2s. How many got 3s? 42. So I want this to be 42 rows. Fill it down. How many got 4s? How many? 30. And how many got 5s? 21. So I have 150 different scores. Now you're probably thinking, well, how the hell do I find the mean of that? Well, I'm going to scroll up here, type in average of A1 through A150. There it is, 2.94. So basically, this was a way to prove that this worked. So the mean score is 2.94. Now, that's going to come into play when we want to calculate our variance. Now, formula for the variance is sigma squared, where basically we take the sum of, we take each score, subtract the mean from it, square it, but multiply it by the probability. Add them all together, there's your variance. Now, standard deviation is just the square root of the variance. So what happens here, that formula looks daunting and scary. So remember, I've actually done this entirely from the ground up. You do not have to do all of this. I am honestly showing you where all of this comes from. So 1 minus 2.94, basically, you're taking the deviation, squaring it, and multiplying it by the corresponding probability. Now, we round those to 4 decimal places at the most. And then you would add them all together. And that's what's going to happen. All right, we're going to come back in 10 minutes, and we're going to start from the ground up again. And first thing we'll do is figure out the probabilities. So, since there's 500, all you have to do is divide each of these numbers by 500. So 14 out of 500 is 0.028. $94 out of 500 is 0.188. 221 out of 500 is 0.442. We take 121 out of 500, we get 0.242. 31 out of 500, 0.062. And 19 out of 500, 0.038. Yeah, there are some people that still don't have television. In reality, this number would probably be more like 1 or 2 at the most in a group of 500. When I was an undergrad TA at Pitt, I worked for Dr. Kleinfall. I mean, wonderful lady. We were actually really great friends. And they didn't have a TV in their house, but her mother lived down the street, so if her kids wanted to watch TV, they had to go to grandma's. All right, so we're going to figure out the mean first. Now, let me just jump ahead. In the next example, we already have the probabilities for that one. Makes things a little. So the mean or expected value, we take 0 times 0.028 plus 1 times 0.188. We don't need to actually calculate them individually. I mean, you can if you want. And I'll show you a calc. In fact, I think I have a calculator trick video. You can do that. It's 4 times 0.062 plus 5 times 0.038. So that is going to be 2.236 televisions. So in my house, I'm above average. My wife, we have 3 TVs. One in the living room, one in the bedroom, and one in my man cave. Now, what I have gone ahead and done here is on Excel, I've actually put the numbers in, and if I do average of A1 through A500, 2.236. All right, so now the variance. Now the variance is going to be a little more involved. So we'll have 0 minus 2.236 squared times the corresponding probability, which is 0.028, plus 1 minus 2.236 quantity squared times what? What was the probability of one television? 0.188. Now, we'll round this to 4 decimal places. Plus 2 minus 2.236 squared times 0.442. Plus 3 minus 2.236 squared, multiplying that by 0.242, plus 4 minus 2.236 squared times 0.062, plus 5 minus 2.236 squared times 0.038. Again, we will round this to 4 decimal places. Now, the variance is the lengthiest one to calculate. So, to 4 decimal places, the variance should be 1.0763. Now, when you do these ones on MyLab Stat, by the way, pay very close attention to the rounding. Now, before I actually do the last one in that standard deviation, here's the variance, and I'm rounding that to 4 decimal places, 1.0763. And the standard deviation is a piece of cake. Why? Just take the square root of the variance. And that measures the spread, so it would be 1.0375. Now, of course, if you gave me 1.0374, I would totally count that. But that's how it all works. So, here's what's going to happen now. I am going to do, so I'm going to show you how we get this, and obviously by hand, you know, you have 2 times 0.15 plus 3 times 0.25 plus 4 times 0.35 plus 5 times 0.20 plus 6 times 0.05. So we get 3.75 is the mean number of passengers. And yeah, so you would think, oh, people, that wouldn't work. Well, this is an average. And no, like our average didn't lose a head or something, or 25% of their body. So, before we do the variance, now, if you've got 3.75, you can start working on variance. I'm going to show you how to do the mean a little more straight up in the calculator. So, I've actually put in list 1 the number of people, list 2 the probabilities. Now, you'll be able to play this back once I post the video. So, I'm going to highlight L3, and I'm going to do, to make sure L3 is highlighted, make sure it's empty, I'm going to do L1 times L2. There's the products. Now, I could honestly add those by hand, but I'm going to show you an easier way. We're going to quit out of this. We're going to hit second and stat, scroll over to math, and we're going to pick sum of list 3. Boom! 3.75. Right there. Makes life a lot easier, doesn't it? Recorder. So the variance, so to do the variance, basically we will do 2 minus 3.75 quantity squared times 0.15. Now, I'm not going to make you write out all this. Like, what I usually do when I write out the keys is I would do like plus dit. 6 minus 3.75 quantity squared times 0.05. So when you add all that up, you do get 1.1875 passengers. Now, I'm going to show you a cool trick on the graphing calculator. So we're going to go back into that stat menu. Now, we're going to go up into L4 here. We're going to open up a parenthesis. So we're going to have L1 minus 3.75 quantity squared, and it's going to be multiplied by the corresponding probability. Well, what list has the probability? The second list. And, you know, you can write those down or whatever, but we can go and find the sum by second list, sum of L4. Boom. That's how it's done. Now, the standard deviation is going to be real simple. All you have to do is take the square root of 1.1875 and we get 1.0897. All right, not bad. So, this one here. So, the probability that there are more than 5 tutors at any given time. So, more than 5 means what? 6, 7, or 8. So, I mean, to tell you the truth, you could just give me the answer and that would be acceptable. But I'm showing you where I get it. You know, 0.20. Now, 6 or fewer tutors at any given time. Now, there's 2 ways that I could do this. I could, you know, 0.23 plus 0.29 plus 0.28 plus 0.13, and that will add up to 0.93. Or 1 minus 0.05 plus 0.02. Take away what you don't want. You get the same thing. So it doesn't matter which way you do it. That's what I like about these probability calculations here. Now, the expected number of tutors in the center at any given time, well, all I have to do here is simply take the number of tutors multiplied by the probability and add it all up. Oh, it doesn't end with 6, it'll end with 8. So the expected or mean number of tutors would be 4.54. Now the variance gets a little more entertaining here. We'll round that just to 3 places. So we'll do 3 minus 4.54 quantity squared times 0.23. And 8 minus 4.54 quantity squared times 0.02. So the variance is going to be 1.508. .508 tutors. And then lastly, the standard deviation, all you got to do is take the square root of the variance. And we get 1.228. So not much spread here. Now, another concept besides, expected, well, this is expected value, but we're now going to get into one of my favorite topics that deals with this, and that's with gambling. Now, I'm not some like degenerate gambler, but we're basically going to learn that the house always wins. So I'm going to guide us through this example here. At a raffle, we sell 1,000 tickets at $2 a piece. Now, the expected value of your game. Now, keep in mind, we're selling those tickets at $2 a piece. Now, I have done this from 2 different approaches. Now, to find the gain for each individual prize, we subtract the price of the ticket from the prize. So we're doing this in terms of the gain. And the probabilities. Now, where did I get 996 from? There were 1,000 tickets. 4 were winners, but 996 were losers. So basically, you multiply the gain by the probability, and you get negative 1.025, or rounding that to a negative $1.03. Now, what this means is, for each ticket you buy, you'd expect to lose $1.03 per ticket bought. Well, of course, raffle tickets, they're not doing this to lose money. They've already set the prizes up, set whatever the prize is going to be. And what they're doing is they're going to make some money out of this. So, let's look at it from, losing $1.02.50, even though, yeah, you do lose $1.03 rounding. We're going to look at it this way. Now, we're going to rewrite the problem in terms of just what you get if you win. So, you could get 500, 250, 150, 75, or 0. Now, what this means is your expected win is 97.5 cents. But how much money did you have to put up for that expected win? Of 97.5 cents. How much money did you have to put up? You had to put up $2. If you take 0.975 minus 2, you get negative $2.50. So on each $2 ticket bought, you would expect to walk away with 97.5 cents. In other words, you'd lose $2 less that. Rounding does mess with the mind a bit here. Now, it doesn't change our variance or standard deviation. So for the variance, basically, what you have to do is calculate this, the prize minus the expected win, square it, and see, that's the thing. We're going to get into some big numbers here. Then multiply it by the probability. And so for this, the variance is $339.67. That's pretty high. And then to find the standard deviation, you take the square root of that. So in other words, it goes to show that there is quite a bit of variance here. Now, this is a $1,000 raffle prize. In a Powerball or Mega Millions, whatever you want to call it, Powerball, trying to find the expected value here. The variance and standard deviation are very high. Now, when the jackpot is very high, the expected value is actually in your favor. Of course, there's taxes, of course, but we're not talking about that. Oh, but the variance gets into the millions. So I'm trying to find out where the variances are. I didn't have that. But yeah, like a positive expectation. Okay, maybe this. No. Okay, I can't find it easily. But now we're going to sell 10,000 tickets at $5 a piece. We're going to work through this one together. So 10,000 tickets at $5 a piece. So we're going to determine the expected value as well as the variance and standard deviation. So there's one winner each of these. Now, there are more complicated examples. So the prize money and probability. So there's one $25,000 prize, one $10,000 prize, one $5,000 prize, and one $2,500 prize. So basically, each of these probabilities is 1 in 10,000. But you could win nothing. Now, what is the probability that you win nothing? $9,996. Because if there are 4 winners, 9,996 losers. So we're going to figure out the expected value here, and we can also approach it another way here. So if we take 25,000 times 1 in 10,000 plus 10,000 1 in 10,000 times 1 in 10,000 plus 5,000 and then 2,500. And there's, of course, the probability of winning nothing. So, when you add all that up, what is the expected win? I'll give you a hint. So when you add all this together, it's going to be $4.25. Now, how much money did you have to lay down to get an expected win of $4.25? You had to lay down $5. So you have an expected loss of 75 cents per ticket. Now, here is another way to look at this. There were 10,000 tickets. Now, total in prizes that are given away. That's actually very simple to figure out. How much is being given away in this raffle? $42,500. Now, what would the total income brought in be? You're selling 10,000 tickets at $5 each. It's just 5 times 10,000. So it is $50,000 income. But you're giving away, yeah, $4.25 is enough to say, but I'm showing you another way that this can be acquired. So if you notice, so we do have a profit on our hands. What is the total profit? $7,500. Now, so here's the thing. If we actually did, the total in prizes, 42,500 over 10,000, what's that going to be? $42,500 divided by 10,000, $4.25. And that is the payout per ticket. Well, we already figured that out. Now, if we did 7,500, which is our profit, and divided by 10,000, that's 75 cents. Lost per ticket. Well, lost to the customer, but gained by the raffle maker. So I just wanted to show you kind of just a cool way that you could also do this. Now, the variance, let's see what the variance is going to be. It's going to be a lot. So we'll take 25,000 minus $4.25 squared and multiply by 1 in 10,000. And add that all the way up to 0 minus 4.25 squared times 9,996 over 10,000. So the variance of something like this So the variance is going to be in 5 figures. $75,606.94. Dang, that's a lot of money. And the standard deviation will follow as the square root of that. So 75,606.94, $274.97. So, yep, there's a lot more variance in this one than there was in the previous one. And one of the reasons that is because the we're going to have 3 different outcomes. One will be your outcome and the money. So one will be black, and you win 10 bucks. The probability of said outcome is 18 out of 38. It could land on red, and you get nothing. 18 out of 38. Or we could land on green and get $2.50. And the probability of getting a green is 2 out of 38. So the expected value, 10 times 18 over 38, plus 0 times 18 over 38, plus 250 times 2 over 38, that is going to be $4.87. So, who still wins? The house is still going to win. Not as much, but they will still win. In fact, what a lot of these casinos will do is, like some casinos in Atlantic City actually had $5 roulette. They didn't have 25-cent chips. They'd actually have to put out quarters. But casinos that do this in Atlantic City and West Virginia now put out a minimum of $10. So we lose 13 cents. That, a 13-cent loss. Basically, that cuts the house edge by half, but the house still has an edge. So, probability that a randomly selected person has 4 credit cards, well, it's just 0.109. Now, at least 2, so we can include 2, and we would just add 2 through 6, or what might be a quicker way? One minus 0.027 plus 0.144. And we get 0.829. So 3 or fewer, 0.215 plus 0.327, 144, 027, we get 0.713. Now, more than 3 credit cards means 4 or more, basically. More than 3. Now, I could actually, let's see here, 3 or fewer or more than 3. I could just do 1 minus 0.713 and get 0.287. So here comes a biggie. So we're going to find the mean number of credit cards. So, you take 0 times 0.027 and you add up all the resulting, the number of credit cards by the probability, and we get 2.81 credit cards for the mean. So that's what we get for that. Now, to find the variance, we would take each number, subtract the mean, square that deviation, multiply it by the corresponding probability, and do that for each one. And the probability of 6 is 0.041. So when you do that, you can also use the graphing calculator. and we get 2.1359. And then it'll simply follow that the standard deviation is the square root of the variance. And we get 1.4615. All right. So that's how we do that one. Now, since there were 10 $250 prizes, we need to, the probability is going to become 10 out of 1,000. And for 0, let's see, we had 17 winners and 983 losers. Now, if we were doing variance and standard deviation, this would really be necessary. So basically, we have 10,000 times 1 in 1,000 plus 5,000 times 1 in 1,000 plus 1,000 times 5 in 1,000 plus 250 times 10 in 1,000, and it's going to be $22.50. So basically, you'd lose $2.50 for each ticket, or basically, the rafflers would gain $2.50. So rafflers would gain a few bucks, but not a lot. Might not even be worth it at this level. All right. So I'm going to let you try these next two. All right, so for this, all right, so for the expected value, you have 4 times 0.23 plus 5 times 0.34, 6 times 0.12, 7 times 0.28, and 8 times 0.03. What do we get for that? 5.54 is our mean number of people. Now, let's say each person would have to pay $25 to take the tour. We're going to find the money made from each group. So if each person, it costs 25 bucks, 4 times 25 is 100. This is 125, 150, 175, and then 200 big ones. Yeah, 25 bucks. It's actually worth it. So when you figure this out, the expected value, not 100 times 0.23 plus all the way up to 200 times 0.03 is going to be $138.50. Now, if you take this $138.50 and divide it by 5.54, what do you get? You get 25. Now, I'm not going to ask you something like this on a test, but this is something that we would actually be doing a lot of in stats too. Basically seeing what a multiplier does to the expected value, as well as the variance and standard deviation, because there are some interesting quirks with that. And that would actually involve the Pythagorean theorem, believe it or not. The most simplest bet at the craps table, pass line. Now, again, how we figure that out? Well, trust me, you will not need to know how to do that. So that's something that would be more of a stats 2. They only offer stats 2 at the biggest community colleges, but they're talking about offering it here. I'll tell you, I would love to do that. So basically, probability you lose is 1 minus that. So 1 minus 244 out of 495. And it's 251 out of 495. Now, if you have an older calculator, you can hit math and enter twice and get the fraction that way. So, to figure that out, 20 times 244 out of 495 plus 0 times, well, it doesn't even matter because you lose. So to the nearest penny, it is $9.86. So that means you would lose 14 cents. So if you took 14 cents, this is the only time I'm ever going to ask you for house edge. The house edge on this is only a 1.4%, which craps is actually one of the, it's even more fair than roulette. Now, that's your standard pass line bet. Now, a single snake eyes bet, which that will pay 30 to 1. Now, what that means is, yeah, like when you saw Brad Pitt put $100,000 on snake eyes, and it pays 30 times that, 30 times 100, 100,000 is how much? Like $3 million. Now, the probability you lose is 35 out of 36. We took this 310 times 1 over 36 plus 0 times it by that. It is, your expected win would be $8.61 or $1.39 loss. For the house edge, $1.39 over 10, that's 13.9% pow. In other words, this is what we call a sucker bet. Anything with the house edge in double digits is truly a sucker bet. Now, the field bet, if you bet $10, it pays triple for a 2, single, and double for a 12. Well, all we got to do is figure out the probability. Well, we already have the probability. 1 in 36 plus 20 times 14 out of 36 plus 30 times 1 over 36 and 0 times 20 out of 36. Guy tried to claim that that pays even money. And it's $9.72 or a 28-cent loss. So the house edge, and this is the only time I will not ask you for house edge, 28 cents over $10, 2.8%. So that's not too bad. It's not too brutal, but so your best bet is to do, if you're ever going to play craps, which it's honestly a lot of fun at a real table. It really is. All right, so how to determine whether a probability experiment is binomial or not. we're going to be able to find binomial probabilities using the formula as well as the calculator, and to find the mean, variance, and standard deviation of a binomial probability distribution. So a couple of requirements are that there's a fixed number of trials, and each trial is independent of the previous one. So a fixed number of trials, that's one thing that is going to distinguish this, particularly between binomial, geometric, and Poisson. So that's the thing you're going to look for here, basically a fixed number of trials. So there's only two possible outcomes of interest. It's either a success or a failure. And that happens in most of our probability situations. Probability of a success is the same for each trial, and the random variable x counts the number of successful trials. So n is number of times we actually repeat a trial, p, or the probability of success, and q is the probability of failure. Basically, it's the complement. And n is the random variable, and x is number of successes, which goes from 0 to n. So a certain surgical procedure has an 85% chance of success. Now, of course, in the field of medical, what is a success? You know, it's kind of hard to measure that. It's that, well, high-risk surgery, especially like a high-risk brain surgery, you know, a success would mean you live. You know, I remember in Pittsburgh, Dr. Starzl, back in the early 80s, performed the world's first heart and liver transplant simultaneously. And the girl that he performed it on lived for another 150 days. Now, of course, I think that was also before our medical, you know, of course, what's the one thing we always worry about when it comes to medical? What's the biggest thing that would prevent us? You know, cost. Does it really cost that much? No. So this is a binomial because there were 8 surgeries. That was a fixed number. 2 outcomes, and probability of success is 0.85. So let's see if this is a binomial. We have 5 red marbles, 9 blue ones, and 6 green ones. We're going to select the three marbles without replacement. So you think this would be a binomial situation? What do you think? No. And here's why. Without replacement, the probabilities will change. So the answer is just a big no. Even though we have seemingly a fixed number, you know, we do this without replacement. Now, if we did it with replacement, that would change everything. So yeah, this is not a binomial because the probability changes. So let's see that the probability that a person randomly selected having a Twitter account is 79%. You know, when I first started teaching this, I don't even think Twitter existed when I first started teaching. I don't know. But let's say we want to find the probability that exactly 3 out of 5. would you say that this is a binomial set? Well, we have 5 fixed trials. There's 5 of them. Probability of success is 0.79. Yeah, it has to be random. We have to randomly choose. Two possible outcomes, probability of success is the same. Yeah, so yeah, this is. Now, how can we find the probability that 3 out of 5 will have a Twitter account? Well, we're going to introduce the binomial probability formula. Now, here's the thing, you will. So one of the things is when you do this binomial probability, you'll be able to use the calculator for a lot of it. And the calculator for the binomial probability calculation. But I want to show you how to do it with the classic formula. So if we let x be the number of successes, p represent the probability of success, q represent the probability of failure. Probability of x number of successes is this. Now this is a factorial sign where n factorial is n times 1 less times 2 less all the way down to 1. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, or 720. 0 factorial is going to be 1, since there's one way to choose nothing. Now, it's true, you can actually use the binomial, you can actually use the factorial button in your calculator. However, we can simplify this by using the n choose r function. And basically, it's a number of ways we can choose r number of objects from a larger group of n objects such that order doesn't matter. So for instance, if order didn't matter, let's say I had 5 letters to choose from. So choosing ABC and CBA would be the same thing in that case. Now, there is another one, NPR, that's permutations. There's actually, so the field of math devoted to this is called combinatorial math or combinatorics. There's actually entire fields of study devoted to combinatorial or counting methods. So, quite a lot. So we can do n choose r. So if I had 8 students and I needed to pick 3, there would be 56 ways to do this. So let me show you. So yeah, you want the choose r function, you go to prob and you do ncr and you would do 8 choose 3. Now, if you have an older calculator, this is what will happen. Let me put that to classic for a minute. You would actually have to type in 8, go to math, prob, and do that. It would show up as 8 NCR3. We're never going to use the permutation here. We're only going to use the combination. So, just for a lark, 8 factorial, if I wanted to do this, prob factorial, and it's divided by 5 factorial times 3 factorial. And you get 56 that way. Or, 8 choose 3. Also, you've ever seen Pascal's triangle it would have binomial coefficients. And as a matter of fact, if you were expanding a binomial, this is coefficients come from NCR. Like we're talking if you expanded like x plus y to the 8th power. That would, and no, it's not x to the 8th plus y to the 8th. But so many uses for all this, quite. But there are 56 ways we can choose a group of 3 from a larger group of 3 people. And such that order didn't matter. But if we wanted to do it such that order did matter, which we never will, that would be 8 permute 3. So you would have to go NPR 3, and that's 336, a lot more. All right, so we're going to work through a very guided example here. Microfracture knee surgery has a 75% chance of success on patients with degenerative knees. The surgery is performed on 3 patients. We're going to find the probability of the surgery being successful on exactly 2. Now, these decimals are long, but they're terminating. Stay with it because it's all, some other things are going to come out. So, if I work this out in the formula like this, I get 3 choose 2 times 3/4 to the second times 1/4 to the 3 minus 2. Basically, 1/4 or 25% is the probability of a failure. And it's raised to the power of the number of failures. So if we had 3 trials, it would be 2 successes and 1 failure. Now, of course, you could enter this just as well in the calculator, 0.75 squared times 0.25 to the first. But this is what we're going to get. Now, you could even do this with a tree diagram where, bless you, you have the number of successes and probability, and we're looking for where the number is 2. These probabilities, and you add them up. So, and trust me, it is going to be a hell of a lot easier to use the formula. But there's an even better way to do it in the calculator that I'm going to show you. Basically, when it comes to these calculations, all you're doing, the probability of success and failure stays the same. All we're doing is changing the x. X is the number of successes. It goes from 0, 1, 2, and 3. We had no successes. We had 3 failures. We had 2 successes, 1 failure. Basically, these powers would be added to 3. Now, I'm going to show you another way, and this is where you're going to find binom PDF. Now, where did you find that in the calculator? Well, you have to hit second and bars for the distribution menu. Now, we're going to be using this normal probability and the t's a little later on. We got to scroll down to binom PDF. Now, with the newer calculators, it's going to prompt you for number of trials. So the number of trials was going to be 3. Probability of success was 0.75, and the x value was 0. So if you binom PDF, now if you have the older one, all that would come up is binom PDF, this, and this. I mean, you'd have to type those in. So 3.75 and then x. So 3 is the number of trials. 0.75 is the probability of success, and x is the number of successes. So if we changed just the last one, so if we had one success, there's our probability. If we had 2 successes, there's your probability for that. And for 3 successes, there's your probability for that. So that's the really short way of using the calculator. Now, you're probably wondering, but there's a binom CDF. We're probably not going to talk about that today, but we definitely will on Wednesday. So, when you do this, all probabilities do add to 1. Now, if we want to find the mean and variance in standard deviation, this is where it's going to be kind of interesting. We're going to use that long method one more time. Then we're going to do then I'm going to introduce something sort of new to you. So for the mean, now it might be beneficial to just, you could also put these in fractions. This is 1/64, this is 9/64, this is 27/64, and so is this. Plus 2 times 27/64 plus 3 times 27/64. So if we did that on our graphing calculator, we would get a very easy 2.25. So for 3 surgeries, we would expect in the long run to have 2.25 successful ones. Now, finding the mean is brutal. If we want to find the variance, what we would do, 0 minus 2.25, squaring that, multiplying it by 1/64, plus 1 minus 2.25, squaring that, multiplying by 9/64, then 2 minus 2.25 squared times 27/64. And then 3 minus 2.25 squared times, yet again, 27/64. You punch in on the calculator, and we get 0.5625. Now, for the standard deviation, it is the square root of 0.5625, which magically happens to be 0.75. Now, if we do, I'm going to have you calculate 3 different things. First off, what was n? How many trials did we have? 3. our probability of success was nope, 0.75. And Q was 0.25. N times P is 3 times 0.75 for 2.25, which magically matches to the mean.
Did you read it right? 2.25 or 0.25?
0.25 here for this one. Here?
Yes, sir.
Yes, that's exactly what I meant.
Okay.
So N times P times Q, 3 times 0.75 times 0.25 is 0.5625, which happens to be the same thing as our variance. And the standard deviation is the square root of that. Now, you're probably annoyed that I made you go through all that calculation stuff. But I want you to know something. This only works for binomial distribution. It has to be binomial for these formulas to work. Now, when you do have a binomial probability question on your test or on an assignment, I am going to ask you for mean, variance, and standard deviation. That's going to be a part of it. And again, this is only the case for binomial distributions. So, yep, binom PDF. Now, binom CDF is where you're finding the probability of X or fewer successes. So, and we'll be using that one probably Wednesday. So remember, any unusual values are going to occur 2 or more standard deviations from the mean. So in Pittsburgh, Pennsylvania, about 62% of the days are cloudy. In a month of 30 days, we're going to see, we want to find the mean, variance, and standard deviation. Also talk about unusual values, which are more than 2 standard deviations from the mean. So the mean is N times P, which is 30 times 0.62 for 18.6. That is the mean number of days. Now, the variance is N times P times Q, which is 30 times 0.62. But what is our value for Q now? Well, remember, if the probability of success is 0.62, Q is 1 minus that for what? 0.38. So we calculate the variance, and what we get for that is 7.068. And the standard deviation basically is the square root of the variance. And for that, we'll get 2.659. Or let's round that to 2.7. Now, here's the thing. Our standard deviation is 2.7. So, we're going to determine our bounds for unusual and usual. So remember that the mean was 18.6. So 18.6 plus or minus 2 times 2.7. So basically, it will go from 13.2 to 24. That is usual. So unusual is below 13.2 or above 24. That would be an unusual amount of rain or cloudy days, rather. All right. I'm going to let you try this next one where the mean for this one would be n times p. Well, we have 180 days, and the probability of success, I wouldn't necessarily call this a success, but the probability that you do write somebody up is 35%. So you would write someone up 63, write people up 63 days out of the year. So n times p times q. So if the probability that you write someone up is 0.35, what is the probability that you do not write somebody up? 0.65, which is going to be 40.95. Or we could call it 41. But the standard deviation would just be the square root of 40.95 or square root of 41. But we're taking this just to the nearest whole number, which would be 6.4 or simply 6. So basically, if we do 63 minus 2 times 6, that would be 51. 63 plus 2 times 6 is 75. So if we wrote up below 51 or above 75 is considered unusual. So all right. Any questions on that? All right. So where suppose that 30% of college-age students have a criminal record of some type, such as underage drinking, shoplifting, something minor. I mean, if you had a major record, you probably wouldn't, but you never know. So here's the thing. The number of students with a record will go from 0 to 8. Now, the probability of success is 0.30. Now, that means the probability that someone does not have a record would be what? 0.70. And how many trials did we have? 8. So here's what we can do. For all of these, we'll binom PDF it. Now, what we'll do is, for part A, we'll actually use the formula and match it up. So, for 0, and I do fear that it's going to get into scientific notation. So 8 trials, probability is 0.3, and we have none. Oh, to 4 decimal places, it will be 0.0576, or you could say 0.0577. So basically, yeah, for 8, we're probably going to get into scientific notation. But that's okay. So we're going to figure out 1, 2, 3, 4, 5, 6, 7, and 8 using our wonderful graphing calculator. Can you imagine where you'd be without this? Yeah. 0.1977. Let's change that to 2. And you can do these on a list too. 0.2965. Let's do 3. Whoops, not plus, but 3. 0.2541. Now for 4, we're going to actually verify this with the formula. We get 0.1361. So one thing that you notice is the probabilities will go up and then go down. They'll hit a peak and then they'll start decreasing again. Now for 5, 6, 7, and 8. .0467. Let's see for 6. 0.01. No, 2.01. For 7, I think we might actually be hitting scientific notation. No, 0.0012. We're close. Now for 8, I think we're definitely going to hit the scientific notation. Yep, 6.561 E negative 5. Now, in case you don't remember your scientific notation, 6.561 E negative 5, it's the same thing as 6.561 times 10 to the negative 5. Now, if we wanted to write this as a decimal in standard notation, we would have to move, well, first we'd have to put some zeros before it and move this 5 places to the left. 1, 2, 3, 4, 5. So basically, we would have 0.00006561, or to 4 decimals, 0.0001. So this might not add up to 1 exactly, but it's, it could be round off or whatever. But to 4 decimal places, we're good. Now we're going to find the probability that exactly 4 students have a record, and showing the work on that. And what I mean by showing the work, we're going to use the binomial probability formula. Now, what I'm actually going to do is I'm actually going to do this completely from the ground up. So in this case, x is 4. So I would have 8 factorial over 4 factorial times 4 factorial, which happens to be 8 choose 4. And if I wanted to figure out 8 choose 4, it's 70. So 70 times the probability of success. Well, how many successes did we have in this particular one? Well, that was the probability of success. We're going to raise that to the number of successes, which is not 8. That's the number of trials. Four successes times the probability of failure, 0.70. How many failures did we have? Well, if we had 8 people, 4 of them have records. How many of them didn't? 4. The fact that these are both 4 just makes it 50-50. For instance, if this were 7, that would have to be 1. And it wouldn't be a 70 in front of that. So 70 times 0.3 to the 4th times 0.7 to the 4th. And we get 0.1361. Guess what? Matches up right there. Now, somebody have a question? So now, 3 or more students having a record, basically, this is where you're going to add things together. And then mean and standard deviation. I'm going to give you a minute on that. 3 or more students having a record. Well, what we can do is, add 0.2541 plus 0.1361 plus 0.0467, 0.01, 0.0012, 0.0001. Now, what we'll get .4482. Now, the other way you could have done this, 1 minus 0.2965 plus 1977 plus 0.0576. Now, answer could be, if it's, let's see, 0.2965. Yeah, we get the same thing, 0.4482. Now, 6 or fewer students having a record, it's definitely easier to just do 1 minus 0.0012 plus 0.0001. For 1 minus 0.0013 or 0.9987. Well, guess what? We are going to introduce binom CDF. So we're going to do binom CDF, 8 trials, success of 30, and this 6 means 6 or fewer. So let's go to the binom CDF. That's 8, 0.3, and 6 or fewer, 0.9987. What this CDF is cumulative density function. Cumulative. PDF means probability density function. Yeah, if you'll notice, you'll see everything in PDF and CDF. We're going to be using the t distribution and binomial and geometric and Poisson. We're not using chi-squared or f. Kind of sucks. I like the f distribution. Actually, I like chi-squared better. Fewer than 5 having a record. Well, fewer than 5 basically means the same thing as 4 or fewer. So guess what? Binom CDF time. So that's one thing these tables don't have. Those tables didn't have binom CDF. I actually, believe it or not, when I was in college taking Stat 1000 at Pitt, University of Pittsburgh, I taught myself the graphing calculator. I didn't have AP Stats in high school, but that's because it was only 2 or 3 years old when I graduated. They didn't offer it. 0.942 or 0.942. More than 2 means 3 or more, which is the same as 1 minus the probability of 2 or less. Hey, wait a second. Didn't we already figure that out? Pay close attention to wherever it might say more than, or fewer than, or 3 or more, or that and less, or that and fewer. If we did 1 minus the binom CDF of 8.3 and 2, let's just see what we get. Same thing. All right, find the mean and standard deviation. Since this was a binomial distribution, look, all you have to do is the mean is n times p. 8 times 0.3 for 2.4. The standard deviation is the square root of 8 times 0.3 times 0.7. And I won't have enough time to explain things, so we'll pick this up on Wednesday. 1.296. All right, everyone. Your first lab for the probability unit is due tomorrow. Any questions, email me or whatever. So the probability that someone passes is 82.3%, or the probability of success would be 0.823. So what we'll do is we'll go to the binom PDF, and there were how many trials? There were 4 trials. Now the probability of success was 0.823. And for this first one, the x value is going to be 0, and we get 9.81 times 10 to the negative 4. Basically, 9.81 times 10 to the negative 4, we would move this 4 places to the left. So 1, 2, 3, 4. Ultimately, we would get 0.00098. So you could say 0.001 or 0.000, 0.001 or 0.0010 is the probability that none of these 4 pass. Well, we're going to do this binom PDF. Now, which of these parameters am I going to change? I'm going to change that 0. Now I'm going to change it to a 1. And I get 0.0183. Now let's see what happens for 2. We get 0.1273. Now for 3, let's see what we get. 0.3947. And then for 4, let's see what we get. 0.4588. Wow. So we're going to figure out the probability that 3 students, exactly 3, pass their EOC. Now, the reason I'm asking you to show me the formula is one of the things is you're going to be demonstrating that you know that the probability of failure, for choose 3 times 0.823, and what power would I be raising this to? What power would this be getting raised to? How many successes? 3. Now, the probability of failure is 1 minus 0.823, which is 0.177. And if 3 students pass, how many fail? 1. Now, you don't technically need to put this power of 1 here, but, if 3 pass, 1 fail. So if we do this, 4 choose 3, times 0.823 to the third, and then times 0.177, even though, raising it to the first power doesn't do anything, I get the same thing. So that's what that's going to be. What I'm wanting you to show me is that you know that you raise the probability of passing to the third power and the probability of failing to the first power. Now, at least 2 students passing their EOC, well, you can just add those probabilities together, 2, 3, and 4. And you get 0.9808. Almost a virtual guarantee, very close. Now, 3 or fewer, there's 2 ways that this can be done. Actually, there's 3 ways this could be done. Since we only dealt with 4, we could do, probability of none plus probability of 1 plus the probability of 2 plus the probability of 3. Or 1 minus the probability of 4, or binom CDF. Now remember, binom PDF is for the individual probability. CDF is the cumulative probability. So there were 4 trials. Let's see, that was 0.823, and we're dealing with 3 or fewer. It's going to be pretty high. Actually, no, 0.5412. You get that either way. Now, probability that at least one student passes their EOC, well, we could add 1, 2, 3, and 4. What's a quicker way? Exactly. You know, we could do 1 plus all the way up to 4, or 1 minus the probability of 0. 1 minus 0.001 is 0.999. All right. Now, for the expected number of students that would pass their EOC, remember, the mean is n times p. And again, this only works for what kind of distribution? Binomial. Very good. So n was 4, p was 0.823. And we get 3.292. Now, the variance is n times p times q. And I would make it crystal clear how many decimal places I'd want you to round this to, but I have it here. Let's see, the probability of failing is 0.177. And for that, we'll just take it to 4 places, 0.5827. And standard deviation, let's take the square root of the variance. That never changes. That's never going to change. And let's just round that to 3 places, and we get 0.763. Now, I didn't get a chance to talk about this in the last class, but the expected number was 3.292, or we could say 3.3. Now, if you go up where the probabilities are, the peak is going to be right around where the expected value is. And that's the case for the previous example, where our mean was 2.4. And if you look, the peak was at 2. So yeah, the mean or expected value is going to be right around the peak too. So that's how that's going to work. All right, so we're going to do another binomial example here. These are fun. So we're going to be binomial PDFing again. This time for this, we are going to have how many trials? We're going to have 7 trials. What's our probability of success? 0.68. And we'll start with 0. And we get 0.0003. Now, let me show you something here for something like this that might actually be a little bit quicker. So we're going to go back into our wonderful graphing calculator. And in L1, we're going to type in 0, 1, 2, 3, 4, 5, 6, and 7. Now, we're going to highlight L2. This was a trick I actually used to type in the formula itself. But I realized it was easier to do binom PDF. So 7.68, but the x value is now going to be L1. that'll make things a little easier. Now, that is going to be on the video, so you can play it back. Yeah, see, I actually learned, I learned this trick as an undergrad, but see, I didn't even know about binom PDF, binom CDF. I actually did the long formula, which would be, oh man, math, oh wait, crud. If I go up here, it would be 7, then I have to do NCR L1 times 0.68 to the power of L1 times, now what's the probability that we don't win? 0.32. And that would have to be raised. Yeah, see, my calculator didn't even have that fancy math print back then. It would be, we'd have to do 7 minus L1. And you're probably thinking, holy crap, but see, the binom PDF makes it so much easier. I didn't actually discover binom PDF till I was doing field experience, doing a practicum in a public school. But nonetheless, this is what we get. 0.0326.
How did you put that into L2? Like from where you put it in and then...
All right, so I'm going to clear this out. Now, this is going to be on video, so you can play this again. So I'm going to go into the distribution menu and go down to binom PDF. 7 trials, 0.68 in L1 value. X is going to be L1. Boom. Yeah, you'll be able to play this back to your heart's content. My videos are good for something. 0.0326, 0.1154, 0.2452, 0.31, 0.3127, 0.2215, and then 0.0672. So yeah, that's how it works. Pretty cool. Yeah, I actually was able to use this trick like when I took graduate level statistics when we had like 100 trials. That was where that calculator really helped. But that's above our pay grade. All right, so we will be doing 7 choose 3 times 0.68. This 0.68 is to what power? Why the third? That's how many times we won. And times 0.32, how many times did we not win? 4. You get 0.1154. So now we can find the probability that we win at least 4 times. So there's a boatload of ways. We can just add those together. Or 1 minus the probability of 3 or fewer. Well, hey, wait a second. 3 or fewer? What can we use for that? 3 or fewer. The binom CDF. So the words of Gary Gilmore, let's do it. .68, and then we have 3.8466. Yep, that seems about right. So the probability that you win fewer than 3 times, well, technically that is 2 or fewer. So we could break out the old binom CDF again, but this time we're not going to be subtracting it from 1. .038. Now, believe it or not, there is actually some other cool things we can do with this. Now, winning at least 4 times, how many of you are familiar with summation notation? Like the sigma notation, did you learn that? Okay, well, then I'm not going to talk about it. Well, basically, yeah, summation, which I think is pretty cool. Find the probability that you win at most 5 times. That's the same as 5 or fewer. So let's binom CDF the hell out of this. And, you know, the formula for binom PDF is what it was. There is no shortcut formula for the CDF. Believe me, I've looked. 0.7113, 6 or fewer times. Well, there's actually 2 ways we could do this. The quickest way is to binom CDF 0.9328. But if we did 1 minus the probability of 7, or 1 minus 0.0672, we get that. How about that? All right, the mean or expected number of wins, well, that's n times p. That is 7 times 0.68. Or 0.76. So if we look here, the peak occurs at 4 and 5. I mean, it occurs at 5 technically. But yeah, see, this binomial probability is pretty darn cool. A lot of great things about it. Now the variance is n times p times q, which is 7 times 0.68 times 0.32. Let's see what we get for this one. We get 1.5232. And standard deviation, square root of that. .2342. All right, not bad here. Now, before we actually go into the next section, which so probability to compute exactly 20 times, well, that's going to just be binom PDF. There were 25 trials. Probability of puking is 0.7, and you did it exactly 20 times. So 0.7 and then 20 times, and you get 0.103. Now, more than 18 times, that really means 19 or more, or 19 to 25. Now, you could figure out the individual probabilities of 19, 20, 21, 22, 23, 24, and 25 and add them together. Or remember 0 to 18 plus the probability of 19 to 25. Well, those probabilities are adding to 1. So the probability of 19 to 25 is 1 minus the probability of 0 to 18. Or in other words, 18 or fewer. So we are going to binom CDF 0.25, not 0.25, I'm sorry, 25.7 and 18. And we get 0.3407. All right, not bad. All right, so let's go ahead and take our 10-minute and we will metric probability now. And today, we'll probably be able to, talk about the Poisson distribution a bit. So the binomial distribution is one of the big ones. Now, binomial distribution has a fixed number of trials. Probability of success is consistently the same. Now, all the characteristics are similar for the geometric one, except basically you repeat a trial until a success occurs. In other words, you keep failing until you succeed. So it's not a fixed number of trials. So if I give you a probability, and I say, like, find the probability that they win or make it on their 6th trial, and I haven't given you a fixed number of trials, it's safe to say you would be dealing with a geometric probability distribution. Now, the calculation is real simple. Basically, if the success occurs on the X trial, you fail X minus 1 times, and then you succeed. So let's say LeBron James makes a free throw shot about 74% of the time. Of course, I think Michael Jordan's the greatest ever. I've gotten this, some people have really gotten in my face about that one. But, yeah, Michael Jordan, come on. He makes a free throw shot 74% of the time. So find the probability that the first free throw shot he makes occurs on the 3rd or 4th attempt. So basically, we will be adding these probabilities together. So the probability that he makes it on his 3rd attempt, now the 3rd attempt means he failed how many times? He failed twice. Now on the 4th attempt, how many times did he have to fail? He had to fail 3 times. You figure out the probabilities and then you add them all together. So, Mike Vanderjet, or Vanderjerk, I like to call him that, for various reasons, he has a 38% success rate on kicking field goals over 50 yards. 50-yard field goal is not exactly a chip shot. Find the probability that he makes on the 1st, 2nd, and all the way to the 8th. So keep in mind, the probability of success is 0.38. The probability of a failure is 0.62. And again, this is a 50-plus yard field goal attempt. So again, that's a hard thing to do. So the probability that he makes on the 1st, well, that's simple. And let's make these 4 decimals. 0.38. probability that he gets it on the second is going to be 0.62 to the first times 0.38. And that would be 0.2356. Notice that also, yeah, there's no like 0th attempt. You have to attempt it. So the probability that he gets it on the third, and notice there's no like N choose R business to deal with. So 0.62, but how many times did he fail if he makes it on the third? Twice. Then he makes it on the third attempt. And we get 0.1461. You know, on the fourth attempt, that means he has to fail 3 times. We 0.0906. The fifth attempt means he had to fail 4 times, 0.0562. So one thing that you notice is the probabilities do start going down rapidly. And so give me a moment to figure out the rest of these. So we get 0.0348, 0.0216, and then 0.0134. Now, if you add all of these, here's the thing. If you actually go to add all of these, does it add up to 1? They're going to add up to 0.9782. Now, I'm not going to ask you for the probability, like what are all these, you know, on a test here, because this one technically could go on forever and ever, theoretically. But the probabilities are going to get so small, like maybe if you added, you know, if you went to maybe 12, probability would essentially be 1. You know, now believe it or not, there is a geometric PDF and CDF right here. Geomet PDF, you know, he makes it, what was it, 38% of the time. And if he makes it on the 5th attempt, 0.0562, right there. Of course, you could have done it 0.62 to the 4th times 0.38, and it is the same thing. So, if we go to stat and edit, now, I don't want to start this at 0, obviously, but if we do L1, you know, from 1, there's actually another way to do this. Like, let's say I want to take it all the way to 15, maybe. I can highlight this and hit list and operations. I'm going to do a sequence where it's X from 1 to Well, let's take it to 20. Step of 1. So you'll see this on the video. Now I can do either geometric PDF let's see, the probability is, what was that, 0.38, and the x value was L1. So we can see here, once we get to like 14 or 15, there, oh, actually, you're still in the digits here. Oh, you could actually really keep going with this. And if you're not as familiar, let's see, that would be 0.62 to the L1 minus 1. Whoops. Times 0.38. Yeah, same thing. Now, if I wanted to add the sum of the 20 attempts, I could go to the sum of L2 here. And yeah, to 4 decimal places, it's not even 1 yet. So I'd have to take it even further. But the point I'm really trying to make here, geometric probability, it can theoretically be infinite. And I'll tell you, let's see what we get here. So probability that he makes it on the first attempt, well, that's easy. He failed 0 times. So basically, the probability that he fails is 0.29. Now, if you actually use the formula, 0.29 to the 0 times 0.71, anything to the 0 power is what? 1. So basically, we get 0.71 out of this. So making it on the second attempt, that means he failed once. So powers of 1, even though we don't really need to put the powers of 1, I'm putting them there. We get 0.2059. Now let's see the fifth attempt. Now that means he failed how many times? 4 times. Sydney doesn't fail much at this. We get 0.005. Now the 8th attempt means he failed 7 times. I think this probability is going to be very small. 0.0001. Now, on or before the 5th attempt, now remember how we have geometric PDF? Well, guess what? We have geometric CDF. We could do geometric CDF. I think it's, yeah, geometric CDF. That's how it's labeled on here on my calculator. It's actually labeled as geometric. And on or before the 5th, yeah, 0.9979. Now, on or after the 4th attempt, well, that one's going to be a little bit more involved. Well, here's the thing. On or after the 4th, so basically, 1st to 3rd plus the probability of 4th and beyond is 1. So basically, 1 minus the probability of the 1st to the 3rd. And that's another geometric CDF. .71. So yeah, 0.0244. All right. So I'm gonna let you try this next one, and I'm gonna make it a clicker question. All right, so this 90-item deal is actually kind of extra information, kind of meant to kind of scare you a bit. So the probability of a defective is 0.21. Now the probability of a good one is 0.79. So the first defect is found in the 7th component. So basically, we have how many good ones? We have 6 good ones. And then we have our bad one. That's actually not the best quality control. If 20% are coming from the factory bad, something ain't right. We get 0.051 or 0.0511, depending on how you decide to round that. All right, so Chauncey Billups of the Pistons, yeah, he makes free throws 88% of the time. So the probability that he misses is 0.12. So he misses the first shot, but makes it on the second time. It's 0.1056. So yeah. So we've studied 2 types of discrete probability distributions so far, and that was, well, the 3 main types. We had your standard one where, I gave you counts. You had binomial, and then you had geometric. But now we're going to get into Poisson. Basically, it consists of counting the number of times an event occurs in a given interval. And it could be an interval of time, area, or volume. And the probability of the event occurring is the same for each interval. So, and the number of occurrences is independent of the number of occurrences in other intervals. Now, the probability of exactly X number of occurrences in an interval is mu, where mu is the mean number of occurrences. Now, this mu, it may be given or you have to calculate. It's mu to the power of x times e to the negative mu. That e is on your calculator. I'll show you how to do that. And it's going to be divided by x factorial. Now, there is Poisson PDF, so we don't have to worry, we don't really have to use this formula. Poisson PDF will get it for us the exact same way. So for this here guided example, let's say the mean number of accidents per month at a certain intersection is 3. So the thing is, mu is going to be exactly 3. And again, it will always be an integer. And sometimes you may have to calculate that. That's okay. So the probability that in any given month 4 accidents will occur, well, so what we have to do here is let x equal to 4. So this solution here, now we can access this on the calculator. Now if I hit alpha and y equals, for the easy fraction button, I would do 3 to the 4th, get past that, and multiply it. Now, where do you get the e? The e is you have to hit second and the natural log times e to the -3. And it's divided by 4 factorial or x factorial. So 4 factorial, we can go to probability, or we could just type 4 times 3 times 2 times 1, or 24, but we do get this. Now, the other thing we can do is if we go to distributions, we can go to Poisson PDF, and wow, they must have updated the operating system. Now, some of you that might have older operating systems may see this, may see a lambda. That's okay. Yeah, they basically mean the same thing. They're learning a lot of the Greek letters. So the mean in this case was 3, and the x value was 4. And when we go to paste that, we get exactly the same thing. So, yeah, mean of 3, and there are 4 occurrences. So for this, we'd have 0.168. Now, let's find the probabilities of all of these. And we could just use Poisson PDF. So for the first one, probability that no accidents occur, 0.0498. And 1, 2, 3, 4, and 5. Now you're probably going to see something kind of neat, kind of weird here. Don't freak out. But we're going to change that second parameter each time. We're going to change that to a 1 now. We get 0.1494. Now for 2, let's see what we get. 0.224 or 0.2240. Let's see what we get for 3. Interesting, we get the same exact thing. Don't be afraid by that. And we've already done the 4, so let's do the 5. We get 0.1008. Now, we've gone 0 to 5. Now, this is like the, what's it called, the binomial distribution in a way where it peaks in a certain place and then it starts going downward. And it has a peak at the mean. Now, if we added all this together, we don't even get anything really close to 1. We get 0.916. And the thing is, here's why. Just like the geometric distribution, the Poisson distribution theoretically can go on forever. With binomial, you have a fixed number of trials. Now with Poisson or geometric, you don't. But eventually the probabilities are going to get sufficiently small to where it gets to be negligible. So if I went to this feature here, went to the calculator, and let's go, now unlike the geometric distribution, we can have zero number of successes. So if I want to go in to sequence this, x, and this time instead of starting at 1, we're going to start at 0. This time I'm going to end it at 20. Now I'm going to do a Poisson PDF where the mean is still, what was it? The mean was 3. And now the x value is going to be L1. So in doing that, we see that even though we stopped after 5 successes, there's really measurable probabilities until we get to about 10 or 11. And then they just get so small that the difference is really, for the most part, negligible. Now, the other thing you're probably kind of freaking out about is, why are these the same? You're going to find that 2 probabilities, if you list 2 of them, if you list them in a table like this, 2 of them will always, depending on the mean and how many successes, the probabilities are going to be the same. So I want to break that down using the formula. Now, again, I'm going over, I'm not going over your heads, hopefully, but what I'm doing is, I want to kind of explain why this is. So if we do probability of 2, now keep in mind, the mean is still 3. So it is 3 to the second times e to the negative third over 2 factorial. Now, 3 to the second is, just if we expanded this out, 3 times 3 times e to the negative third over 2 times 1. Now, you're probably thinking, why did I do that? Well, here's why. If we do 3, we had 3 successes to the mean was still 3, and now it's raised to the third power. The mean is, e to the negative 3 over 3 factorial. So what happens is 3 to the third is 3 times 3 times 3 times e to the negative third. Now 3 times 3 factorial is 3 times 2 times 1. Now, what could I cancel out here? I could actually cancel out a 3, and what happens is, mathematically, we're left with the exact same thing. So this is not a coincidence. This is just how it works. So that is Poisson probability. It's a pretty neat little quirk with this. So now, so the mean, well, there's 900 referrals over 180 days of school. And the mean will always come out to be an integer. So what does this average out to? 5 referrals per day. So in this case, I'm going to have you fill out this chart, but I'm also going to ask a couple of other questions. I'm going to want you to do probability of 3 or fewer. We could do and the probability of 6 or more. All right, I'm going to give you a couple minutes to putz with this. So, since our mean is going to be 5 here, we could just Poisson PDF all of these, or we could just do it in the table. So, and here's the luxury I have. I actually am not going to delete L1, even though this only goes to 8, from 0 to 8. You know, I'm going to highlight L2 and do a Poisson PDF with a mean of 5 this time. And we can tell, yeah, 4 and 5 have the same probabilities. So for 0 referrals, 0.0067, 0.0337, 0.0842, 0.1404, 0.1755, then 0.1755, 0.1462, 0.1044, and then 0.0653. So 3 or fewer, well, that's easy. All we have to do is we could either add all the probabilities, you know, that's 0.1404 plus 0.0842 plus 0.0337 plus 0.0067, and let's see what we get. 0.265. However, one thing you can probably predict that I'm about to show you, Poisson CDF. That exists too. So the first parameter is going to be 5, and the second parameter is going to be 3. So if I Poisson CDF, whoops, there. And let's see, we get 0.265. How about that? Now, 6 or more. Now, generally for a Poisson problem, I'm not going to have students make this chart because they'll say, oh, 6 or more. They would add 6, 7, and 8 and stop. However, what's the problem with that? It's going to keep going on and on, theoretically forever, but not really forever. So 6 or more, well, if we want 6 or more, basically we could do 1 minus 5 or less. So we'll do 1 minus the Poisson CDF with 5 and 5, and we get 0.384. So, and one of the interesting things that we can do, we could even do on the calculator, we could actually set up Poisson CDF on here, or even binomial CDF, or, you know, whatever. Bless you. So this one has, you know, like 3 or fewer, 4 or fewer. So one thing you can tell is, yeah, where it gets ridiculously close, or effectively 1, That's where it is. So, but that's a little above the level, so to speak. All right, so how are you going to know whether a distribution is binomial, geometric, Poisson, or none of these? Now, you don't have the outright information. So the problem's never going to outright say that use this distribution. No. You have to determine that on your own. So for binomial, if you have a fixed number of trials and a fixed success rate, it's going to be binomial. Geometric has a fixed success rate, but it's not a fixed number of trials. And Poisson will happen whenever the mean is given or whenever you need to find a mean. Now, you might encounter a none of these. Basically, a none of these scenario would be like this first example we did, where basically I give you the counts and you have to figure it out from there. All right, so that concludes all new material. So, I'm going to jump around a bit and do probability that he says it in the first episode. Well, basically, first, this is geometric because in this case, I'm giving you probability, but not a fixed number of trials. So, probability that he says it in the first episode, that means there were 0 failures. Basically, it is just 0.67. Now, in the third episode, now that means how many episodes did he not say it? He didn't say it in 2 episodes. And we'll get 0.073. Now, how about the 5th episode? Well, that means he didn't say it in how many? He didn't say it in 4 episodes. I think this probability is going to be pretty small. .0079, or we want to nitpick, 0.008. So at or before the 5th episode, so what we could do is we could, find probability of 1st, 2nd, 3rd, 4th, and 5th and add them together. Or a slightly quicker way, we could geometric CDF it. .9961. Now, at or after the 2nd episode, well, that one looks daunting, like the next 2, but in reality, at or after the 2nd, well, let's see, probability of 2nd plus the 3rd on. Now, wait a second. All we have to do is take away the probability from the 1st, which magically is the probability of failure. Now, at or after the 5th, well, basically, at or after the 5th, probability of 1st to the 4th, we want to take that away from 1. Point 0.0119. Or you could add, 5, 6, 7, 8, 9, 10, all the way on down and do it that way. So what a lot of students typically get confused by is they'll say like, oh, when do I subtract it from 1? Well, basically, if you've noticed a pattern, if I'm saying like at or after something, that's when you subtract it from 1. At or after the 8th episode, 1st to the 7th, plus the probability of 8th or later adds up to 1. So basically, it is 1 minus the probability of 1st to the 7th. And I think this is going to be pretty. Yeah, basically 0.0004. All right, so basically we divided everything by 2,500 to get this. So the probability that a randomly selected cadet will get 4 or fewer, well, we would add 0.1268 all the way down, or we could just subtract 0.3364 and 0.0416. Either way, we're going to get 0.622 for 4 or fewer infractions. Now, at least one infraction, basically 1 minus the probability of none, 1 minus 0.1648. That's going to be 0.8352. Now, 3 or more infractions, so basically 3 or more infractions, we would be at 0.0856, 0.1268, 0.3364, and 0.0416. So 3 or more, that's going to get us 0.5904. Now, fewer than 2. Now, notice I always like to do like 2 or fewer than 2. Now, fewer than 2 basically means 1 or less. And that's going to be 0.2584. Now, the mean number, basically, in order for us to find the mean, we would take the number of infractions times the probability and just add that all the way across the board. So, one thing we could do here is we could actually put it into L4, and basically it's just going to be L1 times L3. And then we go to find the sum of L4 by going to sum, and then L4, and we get 3.0916 for the mean. So it's a good way to do that. Now the variance, and we'll round that to 4 decimal places, basically we would be taking 0 minus 3.0916 squared times the corresponding probability, and all the way up to 6 minus that times the corresponding probability. So we're going to go ahead and put that into L5. So make sure this L5 is in fact highlighted. So it would be L1 minus 3.0916 squared times the corresponding probability. Well, which column has the probabilities? L3. And there's your variance components. So we're going to go and figure out the sum of that. And it's going to be 3.8472. Now for the standard deviation, just take the square root of that. And we get 1.9614. Now, before I stop this one, I am going to show you the other way that this could be done, that the mean and standard deviation can be done in the calculator a little more outright. Fall in tune with the instructions. So I'm going to go to stat and 1 var stat. Now my list is L1, but the frequency list is going to be whatever you have the probabilities in. It could be L2, but which list has my probabilities? L3. So there's the mean, there's the standard deviation. Now, the reason I'm not as big on this is because it doesn't give you the variance. But how could you get the variance? Square the standard deviation, that's it. All right, so I'm going to go